Okay, you have three kinds of elementary row operations. One is scaling a row by k, and we already know that if you scale a row by k, that grows the determinant by k, right? So for any row in your matrix, if you have A, the determinant of A times k is the same as the determinant of A where any row is scaled by k. But the other two row operations also have basic implications for the determinant. That's theorem 4.5 and theorem 4.6 in this section. Now, I'm not going to go through the entire proof. I just want you to think about the idea of these proofs. The idea is that the formal proof is written out in more detail in the book. So let A be an n by n matrix and B be obtained by interchanging any two rows of A. Okay, then the determinant of A is equal to negative the determinant of B. That should be a B. Okay, so how do you see this? The idea of the proof is this. Well, if you think about A as just having a bunch of rows, right? You have A1, and then you have some row AI and some row AJ, then all B is everything's unchanged. A1 to AN is unchanged except for this is AJ, this is AI. Okay? And then this is a kind of creative proof. It says, well, remember that if two rows are identical, the determinant is 0. So 0 is definitely equal to the determinant of this matrix. Let's make the ith row AI plus AJ and the jth row AI plus AJ. Well, then if this is A1 all the way through, these are the standard A's, and this is AN, so these are the only two rows that are sort of unique, but they're identical, so the determinant is 0. But then by linearity, we could break this apart, right? We could say, well, wait a second. So this is equal to the determinant of A1 AI plus AJ all the way to AN, plus the determinant of A1 AJ AI plus AJ all the way to AN, right? So linearity there says this is equal to the determinant of that plus that. But by linearity, I could expand that one and I could expand that one, right? So this is really equal to 4 determinants. The determinant of the one that's A1 AI AN, and we know that determinant 0 because there are two rows the same, plus the determinant of A1 AI AJ AN. Well, what is that? That's really determinant of B. That's exactly B. Then this one I have to expand. Determinant of A1 AJ AI AN. This one was the one that was in order. That's determinant of A. That's the original one, AI AJ. This is the determinant of B, right? AJ AI. And what's the last one when you expand this? Determinant of the one that has A1 AJ AJ. Again, it has two rows that are exactly the same, so that determinant is 0. So what do you have? You have that 0, I'm sorry, I'm leaving that off. 0 is equal to the determinant of A plus the determinant of B. So they must be negatives of each other, right? Okay, so one other result, that's one of the 3 elementary row operations. The type 3 operation is that if A is a matrix and B is obtained by adding a multiple of one row to any other, the determinants are actually identical. That's sort of surprising. But think about this. Let's let A be like it was before, okay? A1, and then you got an AI, an AJ, an AN, and then what are we gonna let B be? Let B be A1, AI, And then instead of AJ, we have AJ plus K times AI. Okay? Well, let's think about the determinant of B. You can just spread it out by linearity there. And so what you get is you get the determinant of A1, AI, AJ, AN, right? That's just determinant A plus K times the determinant of A1, AI, AI, all the way to AN. This has two rows that are the same, so that's 0. So of course, these two things would be the same.